from a hiding spot among the rocks. It's all about function defining form. Now, what about stopping and turning? That's where the other fins come into play. The dorsal and anal fins are the primary set. They act like the keel on a boat, preventing the fish from rolling over or yawing side to side uncontrollably. When a fish is cruising along, these fins are often held erect to keep it on a straight path. Some fish even have spiny, sharp dorsal fins that double as a defense mechanism. So, not only are they keeping the fish stable, but they're also saying, "Don't mess with me." Two potential predators. But the real magic of maneuverability comes from the paired fins, the pectoral and pelvic fins. The pectoral fins, located just behind the gills, are the multitasking superstars. They are incredibly versatile. A fish can use them like brakes, flaring them out to create drag and slow down rapidly. They're also used for steering, like a rudder. By angling one pectoral fin, a fish can initiate a sharp turn. And for some fish, they're used for hovering in place with delicate sculling motions that look like they're treading water. Watch a betta fish, and you'll see its pectoral fins constantly fluttering to maintain its position. Some species, like the gurnard, have even adapted their pectoral fins to walk along the seabed. How cool is that? The pelvic fins, usually located below the pectoral fins, also play a crucial role in stability and steering. They work in tandem with the pectoral fins, helping to fine-tune turns, stop, and prevent the fish from pitching up or down. Think of them as the rear wheel steering on a high-performance car, providing that extra layer of control for complex maneuvers. In some fish, like gobies, the pelvic fins are even fused together to form a suction cup, allowing them to stick to rocks in fast-flowing currents. It's an incredible example of adaptation. So, how does the fish coordinate all of this? It's a complex dance controlled by the fish's nervous system. The brain receives constant sensory information about water flow, pressure, and its own body position, and then sends signals to the muscles controlling each fin. This allows the fish to make tiny, instantaneous adjustments. It's a feedback loop that's happening thousands of times a second, allowing for that smooth, graceful motion we see. This natural system is so efficient that engineers and roboticists are studying it intently. They're creating bio-inspired underwater vehicles that mimic the fin movements of fish. These robotic fish could one day be used for environmental monitoring, underwater exploration, and even search and rescue missions, all by learning the lessons nature has already perfected. Let's look at a few more amazing examples. The flying fish doesn't actually fly, but it uses its massively oversized pectoral fins to glide for incredible distances over the water's surface to escape predators. It builds up speed underwater, launches into the air, and spreads its wings to catch the wind. Then there's the sailfish, which has a huge, magnificent dorsal fin that it can raise or lower. When chasing prey, it can raise this sail to make incredibly tight turns, essentially using it to pivot its body, herding smaller fish into a tight ball before striking. This fin also helps cool and heat its body. Even the texture and structure of the fins themselves are a marvel. They are made of bony or cartilaginous rays connected by a thin membrane of skin. This structure is both flexible and strong. The fish can actively change the shape and stiffness of its fins by controlling the muscles at their base. This allows for a level of dynamic control that rigid, man-made foils can only dream of. By slightly curving or cupping a fin, a fish can generate different kinds of vortices in the water, creating lift, drag, or thrust exactly when and where it's needed. So, the next time you're at an aquarium or looking into a river, take a closer look at the fish. Don't just see a creature swimming. See a masterclass in fluid dynamics and biological engineering. Every flutter of a pectoral fin, every flick of a tail, is a testament to millions of years of evolution, perfecting a system of movement that is elegant, efficient, and incredibly complex. The science of fish fins isn't just about stability, it's about survival, predation, and the beautiful, intricate dance of life beneath the waves. Thanks so much for joining me on this deep dive today. I hope you found it as fascinating as I do. If you enjoyed this video and learned something new, be sure to hit that like button and subscribe for more adventures into the amazing world of science. Let me know in the comments what your favorite fish is and why. See you in the next one. Have you ever wondered about the incredible journey of a salmon? It's a story of survival, epic travel, and a homecoming that defies all odds. Today, we're diving deep into the salmon's great adventure. A life cycle that takes them from tiny eggs in a freshwater stream to the vast, salty expanse of the ocean, and all the way back again. Our story begins in a cool, clear, fast-flowing river. Here, tucked away in a gravel nest called a redd, are thousands of tiny orange-pink eggs. A mother salmon carefully laid them here, choosing a spot with just the right amount of oxygen and protection. For weeks or even months, these eggs develop, with tiny black eyes becoming visible through their translucent shells. Then, a miracle happens. The eggs hatch and out-wiggle tiny creatures called alevines. Alevines are strange little things. They still have their yolk sac attached to their belly,